So welcome to Avoiding Boolean Flags. We'll talk about why it's called that in the middle of the lecture, but for now what I want to tell you is that by the end of the video your tank and the AI tanks will be not applying forces unless they are in contact with the ground, and they'll be moving a lot more sensibly, much more like a tank, and none of this funny flying lark. So see you in there. Okay, so we'll get to why this video is called what it is a little bit later on, but for now, first thing I'm going to do is remove the AI tanks from the scene. So remove both of those. The world outliner may be the most reliable place rather than hunting around in the 3D view. Then the next thing I'm going to do is just do a little bit of tweaking to my tank's physics. I'm removing those AI tanks, by the way, just because we're focusing on our movement right now. We can put some new AI tanks in later. So I want to go to the tank blueprint and observe a couple of things. In fact, let's just show you this in the world first. Notice that if I move along, I'm pushing the throttle. If I let go of the throttle, I keep going at the same speed, seemingly forever. That's rubbish. A tank is going to slow down. So the way you sort this out is you go to your tank blueprint, to the tank root static mesh component there. Scroll down. While you're scrolling down, make sure your collision simulation generates hit events is on. Mine didn't persist from the last video for some reason, so I'll just save that now. And it's under here, linear damping. Play with your figures of linear damping. I'm going to choose 0.5. I tend to do, well, let's see what 0.5 is like before I say I'm going to choose it. So I accelerate away, and I let go of the throttle now, and it comes to a halt in, yeah, I think that's a reasonable amount of time. But pick your own linear damping. What linear damping is a force that works in opposition to the linear motion. It is a force that works backwards at a factor that depends on both the tank's speed, but also on this linear damping factor. Now, let's look at angular damping. At the moment, if we go hurtling off something, we have two fundamental problems when we're in the air. Not that we're going to do too much flying in tanks, because you can't fly a tank, fool, according to the A-team. But one of those problems is that this happens. Forces are still applied when it's in the air. We're going to fix that. And the other one is it spins far too fast for a tank. So I'm going to give it a fair amount of angular damping, 0.8 angular damping. Rotations aren't completely properly handled in these engines. The intermediate axis theorem, if you want to look it up, isn't built in really properly, but angular damping will give us a nice effect where the thing is a little bit harder to rotate than it looks like it was. So if I put enough angular damping in, look what happens as we're in the air. It's a little bit better. Everything's a little bit more mellow. So that's what I'm going to do. On the tank blueprint, 0.5, 0.8 slows things down. I'm going to save this blueprint right now. In fact, I'm going to save all so we never lose anything again. And now we're going to turn our attention to how we are going to decide whether we're grounded or not, and then how we're going to architect this class. Now, don't use a Boolean flag. A Boolean flag is when you're tempted to say, oh, I'm going to set some flag called isGrounded. Just don't do that. The only time you want to use a Boolean is when the thing you're talking about really is true or false, like whether a button is depressed or not, or something like that, but not when you're using it to ask a question at one time, like, am I grounded? So you could be tempted to go, oh, on hit, let's set a flag to say I'm grounded. And then later you read that flag. Well, hang on, that's a bit nuts, isn't it? Because how do you know that you're still grounded when you come to read the flag later? Why not just ask the question at the right time? But to do that, you've got to architect this class a little bit differently. So what I'm going to suggest is that we don't have this class ticking at all, and that we just do everything on hit. So on hit gets called every frame anyway, and you saw that in the logs. They're up here. So, or every frame that the tracks are hitting something, it gets called, right? So what makes sense from a pseudocode point of view is just simply this. What we do on hit is we drive the tracks, and then we apply a sideways force, and that's probably about it. So let's start that process. The sideways force, let's deal with that as it's right in front of us. That code I've just highlighted in tick component is purely about applying a sideways force, and we can't see that. So it's worth extracting it into its own method for self-documentation purposes, and so it can be called easily from on hit. So highlight that lot. On Visual Studio, you've got quick actions, right-click at the top, and then extract function. You can call it apply sideways force. Now, when you do this, notice that it's noticing that you need the delta time passed in there. Okay, so we'll roll with that for a moment. Okay, so what's happening is that tick component is now calling apply sideways force. So that the behavior will be identical to what it was before, but we actually don't want to call it from tick. We want to call it straight from on hit, because on hit's getting called every frame anyway. Okay, well that's all we were doing from tick component, so guess what? We can get rid of tick component, we can turn off ticking in the constructor, and of course we can remove the tick component override in the header file. Let's try all that before we go any further. So that's good news because we've stopped our thing ticking, which is cool. Let me show you the uncommitted changes while we're here. I'm hearing that you like that, so that's good news. That's what I've changed in the tank CPP. And the tank.h is fairly obvious, so I've just removed that thing. Okay, cool. So Visual Studio is popping up. Let's just play the game, make sure it still works. Should work in exactly the same way should the compiler have succeeded. Delta time is an undeclared identifier. Okay, fine. So what happened is the tick event had a delta time inside it previously. Remember, it was one of its parameters, and now we don't have it available. So let's actually change the signature of apply sideways force. Take the delta time out of it altogether, and we are actually just going to cache well, we don't even need to cache the delta time. We can just, where we use delta time here, let's just go get it. Let's just say immediately before that, auto delta time equals get world. Whenever you use get world, ask yourself if you really need to, but in this case, it is a global piece of information, the delta time. It is world scale, so it's fine to reach up to that global scope, get delta time seconds, or delta seconds rather. So just do that. Just get it just before you need it. In fact, I'm going to move this comment up to the top of this method. Then that's it. Apply sideways friction doesn't need to take in a delta time. Works out the required acceleration using the delta time and applies the sideways force. Does that make sense? Okay, let's try it. Let's see if it, let's not cry for how much sense it makes until we've actually got it compiling. So this time I'll wait for it to compile before I show you the code. Just because you love staring at the compiling C++ thing. It looks a bit like Knight Rider, doesn't it? Kit from Knight Rider, that little thing. Okay, so we're refactoring here. So hopefully we're close to compilation all the time, and look, it works the same. Does it? Am I slipping sideways? No, I'm not. So that's cool. Yeah, we've made good progress there. I'll just quickly show you the code changes for those who are interested in the tank CPP. This is what I've changed so far. Bit hard to read, but obviously the red is where I've deleted and the green is where I've added. Okay, so on hit, we're applying a sideways force every frame. We've got rid of ticking. It's pretty good progress. How about this set throttle malarkey? Well, remember that set throttle gets called 4 times per frame, twice from intend move forward and twice from intend turn right. So we need to consume this throttle a little bit in a slightly more interesting way, because you could be intending to move forward and turn right at the same time. In fact, it happens whenever you're using the left thumbstick on the controller, because both of those inputs are kind of mixed together. So we want to make sure that we can't get to a value of more than 1 in total, a total throttle of 1. So let's think about what's going on here. This stuff inside set throttle at the moment isn't setting the throttle at all, really, is it? If you think about what it's actually doing, we can extract this method. It's actually driving the track. And it's taking a throttle. So let's roll with that for a second. Set throttle. Should set throttle just call drive track with a throttle? That is a completely useless piece of refactoring, apart from drive track is arguably a better name than set throttle, right? By the way, for those non-Visual Studio people, when I do that extract function, it is actually adding in all of my header file things that I need for me. So that's kind of it. But if you don't have that, then you're going to need to do it manually. Anyway, when we set the throttle, what I actually want to do is I want to cache this throttle state. I want to keep the throttle state. Bear with me a second. Let's show you why. So what we do is we just go float current throttle, and I'm just going to say equals 0 because I want a sensible default. We put that as a member variable. The drive track therefore no longer needs to take a throttle in at all, so we can get rid of that in its signature. When it asks about a throttle, it's going to use the current throttle. So drive track's good to go now. When we set a throttle, what we want to do is this. We want to say that the current throttle equals the current throttle plus, not plus equals in this case, because I want to break it down further. The current throttle is whatever the current throttle was previously, plus the throttle we're adding in, but we don't want this to exceed 1. So we use a mathf, or fmath rather, colon, colon, clamp, on that, and we restrict the range to -1 to 1. Now we want to be explicit that we want a floating point value out of this, not an integer value out of this, so we're going to just put a float annotation here in between the word clamp and the open bracket. So hopefully that makes sense what we're doing. We're making sure that this current throttle member variable, regardless of whether from movement component we are setting the intention to move forward and to turn right at the same time, it's always going to end up between -1 and +1. Okay, let's see how this behaves now. And if it works, it's all good news. Then all we need to do is go over to the AI tanks and make sure that they are playing the same game by dropping them back in the scene. It's a good idea to refresh them occasionally anyway if we're making lots of changes to them, because you can't be 110% sure that something didn't happen. Remember that the constructor runs on those tanks only when you drag them into the scene, so you can't be 100% sure that they're still going to work after major changes. So what's going on? No movement at all. So you need to just work out what I've done wrong there. Pop back into the code. And of course, what I haven't done is ever called this drive track method. So we're setting a throttle. We extracted drive track out, but I deleted the call to drive track. So where I've commented drive tracks, I'm just going to say drive track. It should be track because we are in a single track, if that makes sense. The other thing we should do while we're here, it's all very well setting this throttle, but the tank's going to, well, let's just show you. I was going to say the tank's going to continue to roll forward, isn't it? Because we never set the throttle back to 0. So one thing I'm thinking while it compiles we want to be doing is here we want to reset throttle, which is going to be trivial, but let me show you the effect of you not resetting the throttle first. So I'm using the left stick on my controller here, and I'm moving around, and it seems to be working fine. Question is, when we leave the ground, now in the air, you see there's no forces going on. Previously, that tank would have flown, but it's not. When it's not in the air, there are no forces. Much, much, much more like it. Now, we are doing movement the hard way with these tanks, of course we are, but that's because there's a lot more learning in doing it this way than me just saying to you, oh, open up a new project in Unreal, use the 4-wheel vehicle, and the section's over. You're not going to learn anything from that. So doing things the hard way, like training with a massive backpack on in the army, often gives you a lot more growth. So let's reset this throttle. That's really trivial. Once we've used it, we're just going to say current throttle equals 0. Sorry, I never did show you the problem with not doing that, so let me do that before I go away. I've let go of the stick now. I'm not touching any controls, and the tank is still going. Why is it not slowing down because of linear damping? Nothing to do with that. The fact is that that current throttle member variable is still pinned at whatever value it was at, okay? That's the problem we're seeing there. So if you set current throttle to 0, we are golden. Let's take a look. Then all it remains is I dump in the 2 AI tanks and revel in the fact that they must behave very similarly to the way my tank behaves. I'm going to say it again because they're using the same movement API. So I'm going to push the throttle forward, then I'm going to let go of it, and the tank comes to a halt under the linear damping, bonza, and then I'm going to drop an AI tank or 2 into the scene and just F11 it and make sure that they can actually move now, and you'll find that they're moving much more naturally. You see, they've got sideways friction, they've got damping, they're still bouncing off these weird imperfections in the terrain. What that is that the colliders of our tracks are sometimes disappearing. But what I think this is that our colliders from our tracks are sometimes disappearing into the floor and then popping back out. I haven't confirmed that yet, but it's not a dramatic problem. It's like you're hitting pebbles or something. So I'm not too worried about it. And the point is that you're getting lots and lots and lots of different ways of using Unreal here. So, congratulations on getting that far. The tanks are working much better. Remember, you can always go to GitHub, my GitHub, in order to find your the code changes. I'll put a link in the resources, and I'll see you in the next lecture.